All right, let's pick up where we left off with activity 1.2, looking at sequences more closely. There are many different patterns that can generate a sequence of numbers. For example, you may have noticed that some of the sequences in the previous activity were generated by performing the same operation using a constant number. In other sequences, you may have noticed a different pattern. The next term in the sequence is calculated by terming the pattern of the sequence and then using the pattern on the last known term of the sequence. For each sequence in the previous activity, write the numeric sequence, record whether the sequence increases or decreases, and describe the sequence by stating the first term and the operation used to create the sequence. The first one has been completed for you. So here's our situations. First, we did positive thinking. The next one, we did family tree. And on the family tree, we had a pattern of 2, 4, 8, 16, 32, and 64. This pattern is increasing. Just going to put I for increasing. The sequence description. Well, our first term began at 2. Then we multiplied each term by 2. The next situation, a collection of squares. We started with 49, went to 36, 25, 16, 9, 4, and then 1. This was decreasing. I'll use a D for decreasing. So here we begin with 7 squared. We decreased each base by 1 while retaining the square. So for example, we went from 7 squared to 6 raised to the second power, to 5 raised to the second power, to 4 raised to the second power. So we decreased our base number while keeping the exponent of 2. Al's omelets. He started out with 150 eggs, decreased by 144, 138, 132, 126, and 120. That was decreasing. We began with 150 and we subtracted 6 from each term. And Donna's daisies. Donna's daisies started at 3, then it went to 4, then it went to 2, 3, 4, 2, 3, and 4. So in this one, you see that it's increasing and decreasing. So Donna began at 3. And we continued with a pattern with 4 and 2 and just repeated that pattern. The Troop of Triangles, Gamer, Polygon Party, and pizza contest. Here's the sequence. You can see whether they're increasing or decreasing and their pattern. Number 2, which sequences are similar? Explain your reasoning. Some sequences are increasing and decreasing by adding or subtracting positive thinking, Al's omelets, troop triangles, gamer guru, polygon party. Some sequences increase, decrease by multiplying or dividing, such as family tree, pizza contests, coin collecting. Some follow neither of these patterns. For example, a collection of daisies, a collection of squares, and Donna's daisies. Number 3, what do all these sequences have in common? All of these sequences are functions. Remember that a function is where the domain does not repeat. There is an exact mapping between the domain and the range. Number 4, consider a sequence in which the first term is 64, and the term after that is calculated by dividing the previous term by 4. Margaret says that this sequence ends at 1 because there are no whole numbers that come after 1. Jasmine disagrees and says that the sequence continues beyond 1. Who's correct? If Margaret is correct, explain why. If Jasmine is correct, predict the next 2 terms of the sequence. Well, if you guessed Jasmine, you are correct. If we continue to divide by 4, then we would have 1 divided by 4, which is 1/4. And if we took 1/4 and divided that by 4, you would get 1/16. So that would be your next 2 terms, and Jasmine is correct. What is the domain of a sequence? What is the range? The domain of a sequence is all the integers beginning with 1. The range of a sequence varies upon the function. Remember that your domain is your term number. Your range is what makes up that term number. If a sequence continues on forever, it's called an infinite sequence. If a sequence terminates, it's called a finite sequence. For example, consider an auditorium where the seats are arranged accordingly to a specific pattern. There are 22 seats in the first row, 26 seats in the second row, 30 seats in the third row, and so on. Numerically, the sequence is 22, 26, 30, which continues infinitely. However, in the context of this problem, it does not make sense for the number of seats in each row to increase infinitely. Eventually, the auditorium would run out of space. Suppose that this auditorium can hold a total of 10 rows of seats. The correct sequence for this problem is so you have 22, 26, 30, 34, 38, 42, 46, 50, 54, and then 58 seats in each row. So this is the first row, this is the second row, there's the third row, there's the fourth row, fifth row, sixth row, seventh row, eighth row, ninth row, and 10th row. So this is your domain, and this is your range. Does the pattern shown represent an infinite or a finite sequence? Explain your reasoning. This is a finite sequence. Each stage results by taking away the bottom row of the pyramid until the pyramid no longer exists. So this is finite. It ends. If it doesn't end, it would go on to infinity. So it would be infinite. Searching for a sequence. In this lesson, you have seen that many different patterns can generate a sequence of numbers. Explain why the definition of a function applies to all sequences. In a function, each independent value has one corresponding dependent value. In a sequence, each term number, which is your independent value, has one term dependent value that it corresponds to. Create a sequence to fit in the given criteria. Describe your sequence using figures, words, or numbers. Provide the first 4 terms of the sequence. Explain how you know that it's a sequence. So for part A, you could come up with a sequence. Your answers could vary. Let's say that I have start out with 27, then it goes to 9, 3, 1, and 1/3, and it's going to continue. In this sequence, you can see that I'm dividing by 3. So even though this pattern could continue, I'm going to end it to show that it is a finite sequence. Part B, create a sequence that begins with a negative rational number, it's increasing by addition, and is infinite. Let's say that I have negative 2.5, and I'm going to negative 1.5. So I'm increasing this by 1. And your answer could vary. So that would be negative 0.5 and 0.5. And to show that it's infinite, well, I'm going to do what I did earlier. I'm going to show that it's going to continue. And that concludes the end of this lesson. Please email me if you have any questions.